My name's Steve Fodor, and currently I had a little biotech group in Palo Alto where we're exploring new technologies. You know, it wasn't a straight path, and you know, my dad in the early years, I grew up in the late 50s, early 60s, and in Seattle. My dad was a physician, and so he always, you know, made sure that there were, you know, microscopes and telescopes and chemistry sets. You know, would bring me home blood smears from his office and stuff like that, X-rays, you know. So we had a house that had a lot of science in it. So, you know, I sort of did that. I actually, when I graduated from high school, I was not going to go into science. It was in the late 60s, and so I was actually somewhat of a anti-establishment type rebel, and decided I was going to go live out in the country. And so I did not go to college right after high school. I went to Eastern Washington and actually worked on a potato farm and grew potatoes for a year or two with a farmer there. And one day I was with the farmer, and you know, we went through the whole process of planting, irrigating, harvesting, and sorting all the potatoes, putting them into bags. And a guy in a truck drives up, and the farmer sells them to the guy in the truck for 35 cents a bag, and he drives them to the store and sells them for 70 cents. And so I said to the farmer, I said, well, why don't you buy a truck? You know, and he didn't want to step on the middleman and all this. And so, you know, I thought to myself right then, and that, you know, if this is really the way the world is, you know, I should go to college. And so I was going to be a farmer. That's what I thought I was going to do. And plus I was pretty tired of working hard labor. But I went to college, and then you know, started to take some agricultural classes and got totally disillusioned with the courses. They sort of taught by repetition. And so I was going to drop out. And my dad told me, well, don't drop out. Just take courses that are interesting to you. And so I started to take a lot of biology, chemistry, and math courses, and got very much interested in science at that point. Well, you know, I came to the end of my undergraduate work and had to declare a major. And so my first major was in biology, actually. And part of that was to complete a senior project, senior thesis-like program. And I met a guy named Arthur Cohen, who actually ran the electron microscopy section at Washington State, which is where I was. And you know, they had electron microscopy facility and electron microscopes that were totally accessible to undergraduates. And so I started to learn how to use those, and you know, it was just fascinating being able to, you know, take a sample that you could see with your eye and then, you know, end up magnifying it, you know, several 100,000-fold to get down to pretty much the limit of what you could do with electron microscopy, which was in the, you know, 10 angstrom or so, at, you know, 20 angstrom range back then. And so, you know, that was fantastic to me. And then I was looking for my project some DNA, because I wanted to try this technique that was called the Kleinschmidt technique at the time, which was basically floating DNA on the surface interface between a layer of cytochrome C, I believe, and the, you know, meniscus of a bubble, and put it again on an electron microscope grid. And I started calling different people, and I ended up finding a guy named Keith Dunker, who was in the biochemistry department at WSU, and he gave me some samples of bacteriophage FD, or M13, which is the same thing. And you know, I took some. He gave those to me and said, "Come on back if you get anything." And so I did them, and I got these gorgeous micrographs. And I brought them back to him, and as I walked in and showed it to him, he said, "Do you want a job?" and because apparently they had been trying for months to get some good photographs. And so he got me interested in this. I stayed at WSU and got a master's in biochemistry and biophysics. During that period, I also met a fellow by the name of Paul Stein, who was a visiting scientist there and from the East Coast. And Paul was sort of an expert in laser resonance Raman spectroscopy. And so I started to learn from him. This was in the days where the first sort of commercial research lasers were becoming available. And so, you know, he taught me a lot about how to work with lasers, how to do some spectroscopy. And that became the basis for my work when I applied to graduate school. At graduate school, I went to Princeton in Tom Spiro's lab. He was an expert in resonance Raman of hemoglobin. But we also, at the time, he had been getting some of these new pulse lasers, these YAG lasers at the time. And he wanted to do some new work in the ultraviolet realm. And so I started to work with actually a guy named Rich Rava, who I became close friends with and worked for many years. But we had some of the first ultraviolet laser light at the time for molecular research. And we did some of the earliest work on proteins and nucleic acids by excitation of the chromophores, both of nucleic acids and amino acids, back in the early 80s. And so, you know, Tom Spiro, who's the lab we were in, that was my first exposure to a very large lab. There were probably a dozen graduate students and probably a dozen postdocs. We had a big facility. But it was there that I really learned, you know, starting to do some innovative things had big payoff. By doing these first early experiments on nucleic acids and proteins, we then put in some grant applications for Tom, and so then that started a whole new funding cycle for Tom's lab. And, you know, these were actually, I thought, pretty easy experiments because when you get to do them for the first time, you always break a lot of ground. You know, I very much enjoyed it. I always enjoyed working with my hands. I enjoyed experiments and making things work. And so this was the big lesson for me. You know, as well as moving from a place like WSU to Princeton, the exposure was much, much larger at Princeton. But the exposure to the larger lab, the lessons that if you're innovative, you develop a new technique, or new data, it opens new doors for you. And so that was a real eye-opener for me. So at Princeton, when I'd completed there, you know, we'd done some very nice work. I was applying for postdocs, and I really wanted to go out to a guy named Rich Matthews' lab at Berkeley. And so I applied there, and Rich said, yeah, you can come. But the moment I got there, he said, well, you have to get your own money now. And so I applied for an NIH fellowship at that time. And I was working at that time, I'd already had experience in pulse lasers, I had experience with generating, you know, ultraviolet lasers and light. And Rich had been working on time-resolved spectroscopy, particularly of bacterial and plant pigments. And so I took on a couple of projects. One was in bacterial rhodopsin, another halorhodopsin, another sensory rhodopsin, and finally phytochrome, one of the plant pigments, over my postdoc time there. But I'd learned a lot more about very, very high sensitivity detection at that point. And, you know, and this is a little bit of a prelude to what we'll get into, but I was working in Raman spectroscopy, which is orders of magnitude less signal than you get, for example, with fluorescence microscopy. And so I'd learned, you know, on probably some of the hardest problems at the time. And so in addition, I started to get a good background on photochemistry there. So, it was a combination of being able to work with light, being able to work with biological molecules, understand high sensitivity detection, and also photochemistry. After working on that for a while, my ambition was to go into academics. So I applied to a few academics spots and got a couple of interviews. It turned out to be second choice in both of those, and so I was going to stay for another year at Berkeley and then reapply. And it was during that period that I actually got a call from Lubert Stryer, who was at Stanford. And of course, Lubert is a very famous scientist. Not only wrote the textbook on biochemistry that was used by practically every medical student for years, but Lubert had done this very nice work in the biochemistry and photochemistry of retinal, of rhodopsin in sight, in vision. And in addition, had done some very innovative things with strep-avidin system for fluorescent tagging. Had done some work with it was very well known for his work with the Forster energy transfer experiments of measuring distances by energy transfer with fluorescent molecules. So when Lubert called, I listened and we chatted, but he said, well, I'm going to take a year leave of absence from Stanford to start this little company called Affymax. And I'd like someone with your background to come join me. He said, look, if we stay for a year, if it doesn't work out, then, we'll see about, where's a good spot for you, sort of thing. And so I thought, well, okay. And so I went down to this little company called Affymax. And, I have to say my motivations were really to go and do some science. My motivations were not at all to create a new company, nor to necessarily even go after what the ambitions of the company were. I was invited by Lubert, and the prospect of doing some great science I thought was great. But when I got down there was this guy named Alex Zaffaroni, who is a well-known biotechnology entrepreneur in Silicon Valley. He had worked on companies like DNAX. Earlier, I've forgotten the name of the company, Syntex, that he and Carl Gerasi and others did. And of course, they came up with a lot of steroid compounds and things that were used for birth control and so on. He started a company named Alza, which did skin patch technology for slow release of things into the bloodstream. And he started this group called Affymax. And so his idea was, now, remember, this was late 80s. And at the time, people had now begun to clone genes and be able to get receptors and so on in pure form. And so his idea of Affymax, and that's where the name Affymax comes from, is from this concept called the affinity matrix. And the idea was that if you had all of the receptors, for example, in pure form, and you could clone these and isolate them in pure form, he'd like to see ways where you could assay those pure receptors against a whole bunch of chemistry. So whether it's natural products, synthetic chemistry, collections, whatever. And so he called this the affinity matrix, because you want to measure the affinity of receptors against chemical diversity. And so we started to play around with a whole bunch of ideas. And as I mentioned, some of them were things like chemical collections, things for like natural products. We were introduced to a whole bunch of really good characters at the point. Guys like Josh Lederberg were there, thinking about cauldron chemistry, what he used to call cauldron chemistry, where you would, cook up a tar like from the tar pits and see what kind of magic compounds were hidden in there. Just some really great, fascinating stuff, remembering that this was actually quite a while ago, before much of this was very popular. One of the ideas, a guy named Leighton Reed said, well, geez, he was infatuated with semiconductor world. He said, isn't there some way that we could use light to direct chemical reactions and put this together? And I thought that was, Lubert and I both thought that was a fascinating idea. And so I started thinking about how to do that. And some of the chemists had some interesting ideas about photochemical protecting groups and so on. Michael Prong was one of them. Dennis Solis was another. Pete Schultz was coming in at the time and had some interesting contributions. And so, I just started to do some really simple experiments. And, how could we do, light-directed synthesis in very precise locations at a microscopic level on a solid surface? When I first went to Affymax, I was somewhat horrified because, it was a startup. I'd been used to now being in pretty well-funded labs, and I went in there and I was given a desk and empty rooms. And, I had to call up on the phone and order, pipettes and tips and chem wipes. And I thought, oh my God, I've just committed career suicide. I've gone to school for the last, freaking 25 years or something. And now, what have I done? I started to do some really simple experiments, built a very, very simple apparatus in the beginning, which was basically a light source, a couple mirrors, and did some things like printed a checkerboard on a piece of paper on a laser printer, and then took a picture of it, and then had the film developed, and I would use that as a lithographic mask and shine the light through it and image that down onto surfaces. And started to do some very basic experiments, derivatizing the glass, working with some chemists to attach these photochemical removable groups onto the covalently linked surface molecules, and demonstrating that indeed we could excite the leaving groups in different areas on the glass in well-defined areas at different resolutions, and actually in a way that was not available to you by printing normally, by putting pipettes down or doing something physical. We could then generate designs on surfaces or patterns on surfaces in direct chemistry through the use of light on a surface. And so we started to work on that, started to build some things on the surface, started as you might expect because of working with Lubert and because of my background, began to use fluorescence as a readout, and demonstrated very quickly that we could start to synthesize molecules on a surface. And we used some very simple peptide recognition systems in the beginning, where we'd synthesize a little peptide that we had an antibody that could recognize. You could fluorescently tag the antibody, and you could show now we could get spatially resolved synthesis of compounds. So I ended up, building then, we had to have a reader. And so I ended up building a laser through a microscope down to a surface with XY stages, then started to do raster scanning and so on. And so you could build up a two-dimensional image of the fluorescence map, if you will, of a surface. And by the way, none of these type of equipment existed back then. There were some epifluorescent microscopes that you could look at very, very small fields of view, but nothing where if you wanted to scan, a couple centimeters by a couple centimeters you could do. And so I built these systems, and then continued to work on making, compounds in different places. We then kind of stumbled upon, say you wanted to build a matrix of many, many different types of compounds, because that was the original ambition. How could you build millions of compounds on a surface? And it became very apparent that, you can't really do it by using millions of steps. And so then the question, how do you actually build large sets of molecules? And so we came up with some primitive ideas on how to build some overlapping sets. And Lubert actually had some great ideas on how to build a sort of a constant set of oligonucleotides or peptides. But it was actually the first experiment that we were doing where we now by hand drew out some lithographic masks. Fabian Peace is another guy, by the way. I should bring this in. When we started to put together a lithographic system in order to make the first what are now called microarrays, we went down to some old junk shops in Silicon Valley and bought some used aligners that were used to make printed circuit boards and so on. And brought this up to our little office building in Palo Alto. We had to chop out some weeds and so on to get this into a room. But we had set it up now with a old lithographic aligner that was used in the semiconductor industry. I had hand-drawn lithographic mask designs that could be used to do some pattern work to synthesize our sort of first arrays. And we had bought, at that point, an ABI synthesizer that synthesized, one oligonucleotide at a time and taken it apart, but used that as a chemical reagent dispenser and plumbed it over to the lithographic instrument with a holder and microfluidics and so on. And so we had all these pieces put together. And then, of course, as I mentioned, we also had the first scanners that were in the other room ready to scan this thing. And so as we started to do the first photolysis, we were going to lay down a particular building block of an amino acid. And then as I turned the micrometer to go to the next region where I was going to do the photolysis, I realized that, well, if I overlapped it on the very next step, not only would I put compound A down and compound B, but I would also build AB. And so I went into Lubert. I said, well, wait a minute, there's something we don't understand. There's this whole field of how do we do these overlaps in order to generate lots of chemical compounds. And so it turns out this got us on a whole path of really thinking about how many compounds can you make and how many chemical steps. And so we had some great discussions about it, and it dawned on us that this was really a very simple binary process, and we had stumbled on to a formalization of the world of combinatorial chemistry. And so we formalized this, and it turns out that you can make 2 to the n compounds in n chemical steps, which means, if you want to make 1 million compounds, no, it doesn't take you 1 million chemical steps. In fact, 2 to the 10th is about 1,000, 2 to the 20th is about 1 million. So it actually turns out that in about 20 chemical steps, you can actually make a diversity of about 1 million. And it just grows exponentially. And we'd actually formalized this. We put it into matrix algebra and figured out how to create the lithographic masks from the matrix algebra. And so it was a very rewarding and very exciting thing. There's a combination of things that goes on. So one is, at that time and that place, we actually set out to invent something, I think. Because we said we want to have something that can do the following. And at that time and at that point, we had a nice bolus of money that was not earmarked specifically for particular things. So I had a tremendous amount of freedom. I could try this experiment. If it didn't work, I could try something else. If I wanted to spend $100,000 to build a nice scanning instrument, I didn't have to ask anybody for permission. I didn't have to write a grant. I didn't have to wait for them to give it to me and to go through the whole review process. And we could talk about that later because that brings in it's not that that's bad. It's just that if you want to move fast and if you've got an idea, you want to be funded in a way that is very, very flexible. And I think that's it. I think a lot of it is the funding. A lot of it is just the culture that you set up. This was going to be a company, but its first main purpose was to invent some new ways to look at biology and new ways to screen chemical diversity. And so our purpose at that point was to not make money Our purpose at that point was to open a new field and to develop new technology. And I think it's academics at the time, that would have been hard, because I think and even today, it's probably kind of tough. There are some places that give you great startup funding and you maybe have a little window to do that. But, it kind of falls into two buckets these days. One is you have a tremendous amount of freedom and not much money, or you have a big project to undertake, and so you're extremely well funded. And then people figure out, well, how do I leverage that into having a little bit of freedom? But this was a lot easier back then in many ways, because this was a brand new area that nobody really had any results in. So, as we started to work on this, one thing I should have said is that it should be obvious right now that we took an approach which was a combinatorial approach, which was a building block approach. And of course, we took our inspiration from nature. Nature creates chemical diversity through the combinatorial assembly of a limited set of building blocks. It does this in the nucleic acids, it does it in sugars, it does it in peptides and amino acids to peptides to proteins, and so on. And so, we took this building block approach. And the two obvious building blocks were peptides and nucleic acids. Both of those chemistries had been worked out, the solid phase chemistry of both of those important chemistries. As I started, and so for the science paper that came out in 1991, a lot of the recognition, because we had the reagents and so on, was done on peptides. But in that paper, we also worked out the fundamental chemistry and methods of doing nucleic acids. And it was very limited, but we enabled the chemistry in that paper. And actually, in the abstract of that paper, we read, and this is what got me very excited, was in the early, this is 1990-ish now at this point, Germanis and Serkanyakov, as well as Andrei Merzabekov, had come up with this idea of sequencing by hybridization. And the idea was, well, let's say I could make a complete set of all the 8-mers. So that's 65,436 or something like that, 64K. And if I could make all of those 8-mers, I should be able to add those 8-mers to an unknown strand of DNA, and then depending on which one bound, I could tell you what that sequence was. And so this was also in the context at the time that everyone was talking about doing the human genome. And wouldn't it be great if we had new sequencing methods and so on. And of course there was Sanger sequencing, which was great and extremely accurate and still a gold standard today. But this was an idea of doing something new and very innovative. And so, as we started to develop out our chemistry and realized that we could make these matrices of high-density chemical compounds, it became very obvious that one of the things we really wanted to do was nucleic acids. It also had a certain advantage because there's only 4 building blocks, whereas proteins are 20. Okay, and so your number of reagents for proteins goes way up, and the medicinal chemists, of course, came up with all kinds of new building blocks all the time they wanted to add into your repertoire. So I started to get to this position where Affymax wanted to be a drug discovery company. They wanted to go on, they wanted to explore peptides, natural compounds, natural products, and eventually be a pharmaceutical company. But when I started to develop out this technology, to me, it was exceedingly obvious the right home for this was in nucleic acids, because there were only 4 building blocks. And then when you looked at something like this SBH technology, sequencing by hybridization, they only wanted to make 65,000 of them. Well, that was a piece of cake. So I knew that was going to be a piece of cake. And so, this was all theoretical, you got to remember. It was a theoretical construct that we should be able to do SBH. And here I had been developing this technology and I read these papers and I said, well, hell, we can do that. And that's a piece of cake. And so I started working on it. Now, that didn't go over so well with everybody at Affymax. Me, I was still, I appreciated the problems they had, and but let me tell you that I started, I think, in July of '89, and we had the cover of Science about 18 months later. So this was very fast moving. I mean, the experiments worked. It just went click, 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 click. And then I wanted to turn all my attention to nucleic acids because I just thought that was the future. And everyone, remember, there was no human genome. People were still arguing about whether they should do the Human Genome Project in 1990. And so through this interaction at Affymax, I had come to make friends with a number of different people, including Ron Davis at Stanford, and told him about what we were doing, and Paul Berg, who was also at Stanford. Now, Paul was, I believe, on the early council or advisors or something to recommend the Human Genome Project. And in 1991, after the science paper, he invited me to come give a talk in front of, there was Jim Watson and I think this was in Concord or something, but it was a huge panel of people that wanted to go after, that wanted to sequence the human genome. And so they were very interested in alternate sequencing technologies. And I'll never forget this because Paul invited me to go speak in front of these guys. And you have to remember at this point, I got spoiled very quickly at Affymax because because this program was so successful, they basically gave me Alex Zaffaroni gave me all the money I wanted. And although it wasn't fitting into the ambitions and what everybody wanted to do from a business perspective at Affymax, the science was just so cool that Alex just kind of protected me and made sure I had the funding I needed to pursue these things. So when I went in front of the panel for the Human Genome Project, I showed what we have done, and I also showed them what I thought we could do in terms of building arrays of nucleic acids. And I remember Jim Watson at the time, and you have to remember, it's very commonplace now. Everybody knows what an array is, and everybody is used to array formats. But back then, nobody was, because it was all brand new. And so I had these nice scans and pictures of these fluorescent maps of these compounds, and I was showing these, and Jim Watson was watching this, and he finally stopped me in the middle of my talk. And he says, wait a minute. Is this real data or are these just pretty pictures? and I was very indignant at the time, and I said, well, just pay attention, and so, he, if you know Jim, he was very crotchety about the whole thing. Here were all these guys that were very serious. So I was completely a newbie at this and very naive, but coming at it from the technology side and from the sort of science of technology side. And knew just very clearly, had a very, very clear vision that we could accomplish this. And so, we talked about it there. I was just barraged with questions from the group, and people wanting to know, how you're going to solve repetitive elements, how are you going to solve the branch structures, all this sort of stuff. I actually remember Jasper Ryan was there. That he asked some very pointed questions, but not from an evil perspective, from a very constructive perspective, but very hard questions. And I basically said, I don't know. I said, I do not know. All I know is that we will make these things and we will test these ideas. And that was my attitude. There was complicated politics around the whole genome project and all the people involved, and everybody had their own idea about the directions they should go. But I was looking at it from a little bit different perspective, because by then, I'd really realized, for example, we knew that we wanted to make things on the order of 30 bases long, because they gave very nice stability, and you could actually do single base pair mismatches with something of that size. And so it was, but 30 long, that's a number like 4 to the 30th. I mean, that is a really, 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 really big number, okay? And 2 to the 60th. I mean, I'm not even sure how large that number is, but it's ridiculously large. But the thing is that combinatorially, you can make all 30 mers in 4 times 30 steps, or 120 steps, which means you can make any subset of them. And so I started to think about this more as an information technology, that what would really happen is that the genome would be sequenced, and then we could copy basically the genome down onto these chips, and then you'd have a format to look at many genomes. And that was the direction that I was going. Well, there were 2. There was one, you could make these complete sets of 8 mers, 10 mers, and so on, and say, could I do sequencing by hybridization? And then you could also make arrays that were designed as basic memory devices against certain pieces of DNA.